All right, so welcome everyone to the last talk of the fourth day of the conference. And it's my pleasure to introduce Professor Jan Biringer from Boston College, who will give a series of 4 lectures. And in today's lecture, he'll tell us about the Chabauty topology. Okay, please go ahead, Jan.
Well, thanks very much for the invitation and for the warm welcome here. So maybe before I start, let me just encourage everybody to, ask questions as much as you want. In this mini course, we're going to study invariant random subgroups of continuous groups to build on Miklós's work in the discrete case. And we'll also talk about the sort of geometric analog of such invariant random subgroups, namely unimodular random manifolds. But today we're just going to, talk about the space on which invariant random subgroups live. So that's the set of closed subgroups of a group endowed with the Chabauty topology. So, all right, so that's today. So I think I'll start pretty general and just let X be a how about a locally compact metric space. Some of these definitions I could do for an arbitrary topological space, but I am deeply uncomfortable working with anything that's not a locally compact metric space. So we will always assume that that's the case. Okay, and then let's let like C of X be the set of all closed subsets. Okay, and then the Chabauty topology on this set of closed subsets it's the topology that's generated by the following open sets. So I can take like the open set U of K. So here K is like some compact subset of X. And like for each compact subset of X, I can make a basic open neighborhood for the Chabauty topology, which just includes all A in all A that are closed subsets of X that don't intersect K. Don't intersect K. And then so that's one kind of basic open set, and the other kind of basic open set is like, we call it V of U, where U is an open subset of X. And this is just all A in C of X, where A does intersect U. Okay, so yeah, and so what are we trying to do? Like, I'm trying to define a notion of when two closed subsets of X are close. And so it makes sense that, if you have some compact subset here, then this U of K should be an open set, right? Because like if I take a closed subset that doesn't intersect this compact set, and I wiggle the closed subset slightly, it still shouldn't intersect the compact set. Okay. And similarly, if I take a closed subset that intersects an open set, so I have like this little ball somewhere, and then I have this closed subset that intersects it. If I wiggle the closed subset a little bit, then it should still intersect the open set.
Jan, there's a question in the chat by Ali Kazili. Okay, maybe you can take a look.
I will.
Or should I? I can read out. So the question is whether this topology is equivalent to the Feld topology.
Yeah, it's equivalent to the Feld topology. In like, right, in whatever. I don't know. Do they define, like, is Feld topology usually defined in this generality? Yeah, but yes, it's equivalent to the Feld topology. So yeah, okay. So you have these two types of basic open sets, and then maybe the way that I actually think of the Chabauty topology though is in terms of convergence. So so if I have like open sets Cn going to C, so this happens. All right, so this convergence in the Chabauty topology happens if and only if the following two conditions are true. So any x in C is the limit of a sequence of points xn in Cn. And so two, any accumulation point of a sequence xn in Cn lies in C. Okay. Yeah, and so I think it's instructive to just have an example in mind, right? So, and you know, one nice example is I just take x equal to R2, and then you know I say, like, if I look at lines through the origin, you know, at angle theta with the horizontal, they converge to the x-axis as theta goes to 0. Okay, so line, 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 et cetera, converging to the x-axis. Okay, making sense? I would like to actually be able to see the chat. I just forget how to access that when I'm in screen sharing mode. Let's see. Show chat. There we go. Aha, there we go. Somebody asks, is there anything distinguished about compact subsets of X as points of C of X? I don't know. I guess I don't know. Nothing comes to mind at the moment. Yeah, I don't know. I don't think. Not really. Maybe. So, all right. So, what are some relevant facts here? So the first one is that this space of closed subsets is always compact. Okay, so I mean, this is an easy exercise. You can prove it in a paragraph. So yeah, and then so I should mention that if X is itself compact, so if I start with a compact metric space, then the Chabauty topology is induced by the Hausdorff metric. Okay, so the Hausdorff metric, you might recall, is the metric where so DH, H is for Hausdorff, between two closed subsets is the infemal epsilon, such that A is in the epsilon neighborhood of B and B is in the epsilon neighborhood of A. Okay, so here like two sets are close if they're in small neighborhoods of each other. But you should, I guess, notice that like just using the Hausdorff metric doesn't work for general X, because like if you look back at the R2 example, then these lines to the origin at angle theta are converging to the x-axis, but the Hausdorff distance between any line through the origin and the x-axis here is always infinity. Okay, because there are always points on this line that are very far away from the x-axis. Okay, but that said, you can also metrize the Chabauty topology. I mean, you can do it in a lot of different ways. Maybe one that I'm particularly partial to, because it illustrates the relationship with the Hausdorff metric, is as follows. So let's assume X is proper for a moment. So proper here means that closed balls are compact. And then let's pick some P in X, some point P. And let's let dr of A, B be the Hausdorff distance between the subsets A intersect BPR and B intersect BPR. Okay, so I have this right, so closed balls are compact, and so if I take two closed subsets, I can then intersect them with this compact ball BPR, and I can look at their Hausdorff distance. And then you can write the Chabauty topology. So this is induced by the metric where the distance between 2 points, A and B, is just the integral from 0 to infinity of, say, like e to the minus r dr AB dr. Okay, so I mean, yeah, this is kind of a cute formula for for a metric inducing the Chabauty topology. I mean, I guess I wrote this down in like 2017, but there are lots of other metrics that you can make. Yeah, but I guess I like this because it indicates that so the fact that you have this e to the minus r scaling factor. So what that does is, if we look back at the R2 example, sort of at the top of the screen here, then the e to the minus r sort of allows, in a convergent sequence of closed subsets, it allows points that are far away from from your base point P, so like, I don't know, far away from, say, the origin in R2, it allows those points to sort of converge to points in the limit closed subset more slowly. So which is exactly what happens in this sequence of lines. Somebody asks, what happens if X is not proper? Can you define a similar definition? Well, I don't think that this exact thing is going to work very well, because if it's not proper, then you could have, I guess, well, I don't know. Yeah, I guess I'd have to write that down. And maybe, yeah, I guess it's not completely obvious that this doesn't just work without the properness assumption. No, it probably doesn't, though. Yeah. Okay. Well, something to check. So, yeah, it's a good question, though. All right. So, like, okay. So right. So C of X is compact. We've now shown that it's metrizable, or we've said it's metrizable. And maybe I'll just make one remark about it, which is that this space C of X is, even before we start talking about groups, like the space C of X is kind of cool and interesting. And so let me just remark that there's this nice theorem by Curtis and I realize I've never pronounced this person's name before. Shori, or I'll say Shori for now, but I'm sorry if it's wrong. So Curtis and Shori in 774 show that when X is any, say, compact, connected and locally connected metric space with at least 2 points, then C of X is homeomorphic to the Hilbert cube. Okay. Yeah, so it's kind of a lovely little theorem. Yeah, these spaces, they, in infinite dimensional topology, these kind of spaces, I guess, are called piano continua. And whenever you have such a space, then right, your C of X is homeomorphic to the Hilbert cube. Yeah, I mean, I don't know much about infinite dimensional topology, but I kind of like this result. And I guess, maybe part of the point here is that in infinite dimensional topology, there's a lot of flexibility. And so sort of many, many spaces sort of end up being homeomorphic. But this is kind of nice. Okay. So let's start talking about groups then. So when G is a topological group, so I mean, mostly, I think basically all examples that I'm going to ever do are G is actually a Lie group, but you can make the definition in this generality. Well, okay. I guess actually the way I think I chose to define the Chabauty topology, where X was a locally compact metric space. So, at least I want to assume here that G is locally compact, second countable. But the subspace sub G inside of C of X, or C of G now. So this is the subspace of closed, not just subsets, but subgroups. Of G. So this is often called the Chabauty space of G. Okay, and then maybe the first thing to note about it is that sub G is closed in C of X. Hence, since C of X is compact, then that means that sub G is compact. Okay. Yeah, in proving that it's closed in C of, I keep writing X, is closed in C of G, hence compact. Right, and proving that it's closed in is pretty immediate. I mean, basically just because multiplication is continuous, so it sort of passes through the limits in the definition of the Chabauty topology, or rather in the sequence interpretation of the Chabauty topology. Okay, so maybe as a remark here, so why am I calling this the Chabauty topology? Well, so yeah, like what did Chabauty have to do with it? So Mahler's compactness theorem says that for every epsilon and v, so I can look at the set of lattices, right? So lattices are subgroups isomorphic to Zn, or well, discrete subgroups isomorphic to Zn. In Rn. And I can look at the set of lattices with, so one, the norm of V is always at least epsilon for all V in L, like obviously except the origin. I guess that's L, all lattices L, such that there aren't any non-trivial points near the origin, and also the volume of the quotient is at most V. And so Mahler's compactness theorem says that this set here is compact. And okay, what does compact mean? I could just say in the Chabauty topology, but like for when you're just looking at lattices in Rn, like you can define convergence without explicitly mentioning the Chabauty topology as we did before. Like convergence of lattices to another lattice just means like you can pick generating like a basis for the lattice that where these bases converge to the limit basis. And so Chabauty's initial interest in all of this, so this was like in 1950, I think, so introduced the Chabauty topology to generalize Mahler's theorem to lattices and other groups. Okay. So he proves a very similar statement to this for for lattices and like for instance, for instance, like, lattices and simple Lie groups, which are often the ones that come up in practice. So, okay, so that was the history here. So, all right, so let's do an example where we try to understand sub G. So I claim that if I look at sub of the real numbers, okay, so here we're viewing the real numbers as a group under addition, and I want to look at the space of closed subgroups of it. So I claim that that is homeomorphic to just a closed interval, and I'm going to write the closed interval as like 0, infinity, say. And how do you see that? Well, the point is, like, what are the closed subgroups of R? Okay, so there's R itself. Then there's also like AZ, where A is greater than 0. And then there's also just like the identity. And then I can draw a picture of 0, infinity like this. And right, and then you can map sub R to this interval by just sending R to 0, sending like AZ to A, and the identity to infinity. Okay. And to just like sort of convince yourself that this is a homeomorphism, you can think about like what happens to the subgroups AZ as A goes to infinity. Okay, well, as A goes to infinity, the subgroups AZ, they become more and more sparse. And so somehow in the limit, the only element of the subgroup that you can really see is like the identity. Okay, because the other ones all sort of like go off to infinity. And so that's why you converge to the identity as A goes to infinity. And similarly, if A goes to 0, then the subgroups AZ sort of fill out more and more, fill out R more and more densely. Okay, so then in the limit, you get actually the real numbers. All right, so I mean, this example might make you think that the structure of sub G is kind of not very complicated. But there's this lovely theorem that says that even if you just go up one dimension and talk about R2 instead of R, then you get interesting topology. Okay, so this is a theorem of Hubbard and Borezza in 78. And so they prove that that sub R2 is homeomorphic to the 4 sphere. And moreover, so I can look at the set of lattices. So you remember these are discrete groups that are isomorphic to Z squared. And I can look at them inside of sub R2. So if I look at the pair sub R2, okay, so that's a 4 sphere. And then I can look at how the lattices, the set of lattices sits inside of that. It turns out that that's actually homeomorphic to the suspension of the pair S3, S3 minus the trefoil knot. Okay. So, right, so sub R2 is a 4 sphere, i.e. the suspension of the 3 sphere. And then the way that L sits inside of sub R2 is as the suspension of the trefoil complement. Okay, so I don't know, I think that's kind of lovely. And, you know, maybe just as a quick remark on this, since, you know, there's a lot that you can kind of understand quickly here, even if you can't prove the entire theorem really quickly. So, you know, what are subgroups of R2? You know, they're isomorphic to either what, Z, R, Z cross R, Z squared, or R2. And so this is like closed subgroups. And it's, you know, it's easy to see that the space of lattices is 4-dimensional, right? Just because, you know, how do you specify a lattice? You pick 2 generators. So that's 4 degrees of freedom, because and the complement is 2-dimensional. Right, and maybe the the one thing that sort of seems to surprise people, you know, when they're first thinking about this is like, why is the space of Z cross R subgroups 2-dimensional? You know, e.g., there are 2 degrees of freedom in specifying a subgroup isomorphic to Z cross R. And I mean, the reason for that is just like, okay, what's a subgroup isomorphic to Z cross R look like, right? I mean, it looks like a bunch of parallel lines. And what do you need to specify in order to get a bunch of parallel lines? You need like the angle that the lines make with the horizontal, and then you also need the distance between the lines. Okay. And so, and this all sort of jives with the description that I'm giving you, right? Because the space of non-lattices is going to be like the suspension of the trefoil, which is 2-dimensional. I mean, really, it's a 2-sphere embedded in S4. Okay. And then I think it's also worth saying that so, you know, you wonder where the trefoil comes in here, and you know, the statement about the trefoil. This is related to the fact that that if I look at unit area lattices, in R2. Okay, so unit area lattices in R2 I can represent as the quotient of SL2R mod SL2Z. Okay, just because, you know, SL2R acts on unit area lattices, and the stabilizer of, you know, like if, right, the stabilizer of like the integer lattice is SL2Z. But then SL2R mod SL2Z, this, you know, if you know some hyperbolic geometry, you can identify this with the unit tangent bundle of the hyperbolic plane mod SL2Z. Okay, so this is, you know, you look at SL2R acting on the hyperbolic plane via fractional linear transformations, and right, and like the tangent bundle to, or the unit tangent bundle to H2 is sort of identified with SL2R. So if you make the quotient by SL2Z, then you get this unit tangent bundle of this. So this is the modular orbifold. And it's sort of well known that this is the trefoil complement. Sort of for the reason that both the trefoil complement and the unit tangent bundle of the modular orbifold are sort of obviously ciphered fibered spaces. In like, if you know what these words mean, then you know that both these things are ciphered fibered spaces, and you can calculate that they have the same invariance, which implies that they're the same. They're homeomorphic. So this is sort of like, level 0 three-manifold topology. So, I mean, okay, if you don't know what a ciphered fibered space means, essentially I'm saying that both the trefoil complement and this unit tangent bundle of the modular orbifold are sort of obviously circle bundles over an orbifold in some way. And they're circle bundles over an orbifold. I mean, you can check that the base orbifolds are the same. They're both like the modular surface, and also that the bundles are the same. Okay. So, yeah, and maybe I should just say, like, as a remark, in higher dimensions, sub Rn isn't a manifold anymore. But there's some work done on it. So in particular, there's this paper of Kluckner from 08. So he shows that it's a stratified space. And is simply connected. Okay, I mean, the fact that it's like stratified in some sense should be kind of, clear from the definition, because, you can classify all the different types of subgroups in Rn by their isomorphism type. And like for each isomorphism type, it's easy to describe the space of subgroups with that isomorphism type. And so then you're just sort of patching all these different spaces together in some way inside of sub Rn.
There's another question in the chat.
Isn't the space of lattices in Rn dense in sub Rn? Yes. Mm-hmm. Okay. So, yeah, and so maybe I'll just also refer you to, and there's a lot of work on Chabauty spaces. So see also, for instance, there's this nice paper of Bridson, de la Harpe, and Klepsin from 08, for lots of other examples, including they describe pretty well the Chabauty space of the three-dimensional Heisenberg group. Okay, any questions?
You can also see that that quotient SL2 or over SL2Z is complement of a trefoil not directly, right? Because SL2Z is the fundamental group of SL2Z is like xy x square equal to y cube equal to 1, and so I mean so the action is fixing some trefoil knot in SL2.
Mm-hmm. Yeah, that's right too. Mm-hmm. So yeah, so let's do so I want to change gears then a little bit and show you how to interpret Chabauty convergence in terms of something to do with manifolds instead of groups. So this will be a perspective that's useful for the rest of the talks that I'm going to give. So maybe we can call this section like groups versus framed manifolds, or framed X manifolds even. So let's suppose that G is a semi-simple Lie group. I guess, okay, so non-compact. And then K and G is a maximal compact subgroup. And X is the quotient of G mod K. So this is the associated symmetric space. Which we endow with a left G invariant Riemannian metric. Okay, so I mean, you know, if you don't know much about symmetric spaces, that's fine. You can just keep the following examples in mind the whole time. So I could take G to be, I don't know, why don't I just use the isometry group of hyperbolic space? Then K in G is sort of a copy of ON, and X is hyperbolic space. Right, so here, like, all you're doing here is you're just taking isom of Hn, which, you know, acts on Hn, and then you're modding out by the stabilizer of a point to recover Hn. And then you'll also need to have perhaps the example of G equals SLNR, and then here the maximal compact would be SON, and X is the quotient. And you know, you can think of it different ways. Turns out one way you can think of it is like the space of you know, positive definite quadratic forms on Rn. But it won't really matter to for you to have a sort of geometric interpretation of that X in these talks. And maybe just as a quick fact, so whenever you have such an X, X is always so a manifold with non-positive sectional curvature and is diffeomorphic to R to the M for some M. Okay, so I'm giving you this general setup where we're constructing this particular type of Riemannian manifold that it's just a, you know, it's diffeomorphic to Euclidean space, but has some weird metric on it that's that has non-positive curvature. Okay, but yeah, as I said, if all this is unfamiliar, for the most part, you can just always think of the hyperbolic case. So let's let, so I have a G now, so let's let sub df of G so that be the set of discrete torsion-free subgroups of G. And then, so if you have some gamma in sub G df, so you can show that, you know, gamma then acts, because of the discreteness and torsion freeness, then gamma acts properly discontinuously and freely on X. And so you get that the quotient M equals like X mod gamma is a Riemannian manifold. So it's a manifold, and then, you know, you can project down the Riemannian metric from X to a metric on the quotient to get a you know, metric that's, you know, locally isometric to X. and we call such M X manifolds. Okay, so I'm making a class of manifolds by taking this fixed symmetric space, like for instance hyperbolic space, and then quotienting out by the action of discrete torsion-free subgroups. Right, so e.g. HN manifolds are just hyperbolic N manifolds. Okay, and then my question is, now if I have a group, I can quotient out and get a manifold, and so presumably you should be able to see the Chabauty topology via the quotient manifolds. And so how do you do that?
Sorry, Ian, there's another question in the chat.
Is right, if sub df a closed set? It's not a closed set. Like you can imagine, like take you can have a sequence of cyclic groups, for instance, that converges to a group that's isomorphic to R. Like imagine, so in hyperbolic space, for instance, you take a sequence of groups that all sort of cyclic groups that all translate along a particular axis, and then have the translation length go to 0. And then you get a sequence of groups that converges to R. So I mean, this is kind of the same as the example of like AZ converging to R as A goes to 0 that we did earlier. So it's not a closed set, but actually for the most part, like in most situations that you care about, it actually is closed, because if you have a sequence of like in the hyperbolic setting, at least, if you have a sequence of what are called well, no, it's not quite true. Let me just say that there are lots of situations in which you can ensure that a limit of discrete torsion-free groups is still discrete and torsion-free, but it's not closed in general. So yeah, so let's try to understand convergence of discrete torsion-free groups in terms of the quotient manifolds. So so definition. So a framed Riemannian manifold so it's a pair M comma F, where M is a Riemannian manifold, and F is a sort of a base frame. So what's a frame here is just an orthonormal basis for some tangent space. Okay, so you have some point on the manifold and you have an orthonormal basis for that tangent space. And then we say that a sequence like Mi Fi converges to MF in the smooth topology if there exist bigger and bigger radii Ri, and then embeddings like phi from the ball in M of radius Ri around F Okay, I mean, I'm going to write F here, but really, like, you should understand this as like F is an orthonormal basis for the tangent space at some point. This is the ball around that point. Okay, this is the ball around the base point of F. And I want these embeddings into MI such that so these phi's push forward the F frame to the Fi frame, and also that if Gi and G are the Riemannian metrics on on the different manifolds, I'm also requiring that if you pull back using phi, the Gi metric, then that converges, like in the C infinity topology on tensors, to G. Okay, so this is probably a lot to process the first time you see it. But what am I saying here? So first of all, how do you think of? Let's just think of the last statement. So I have these embeddings from like big balls in M into the approximating manifolds, and the last statement is saying that those embeddings are almost isometries for large I. Okay, if like the metrics, so the statement that you're pulling back, you pull back the metrics, the metric on MI, and you get something that's like smoothly close to the metric on M. That's saying that your phi's are almost isometries, and it's a little bit more than saying it's more strictly more than saying that the phi's are like by Lipschitz with by Lipschitz constant close to 1. It's sort of saying that the derivatives of all the phi's are also close to what they'd be from an isometry. So yeah, so I mean, okay, so these phi's are like almost isometries, and so what you get is like this almost isometry of like a big ball in M into the approximating manifolds. And we're also sort of normalizing these embeddings so that they carry the base frame of the limit manifold to the base frames of the approximating manifolds. And I think it'll be most helpful to have just an example to think about in mind. And here's sort of the picture. Okay, imagine that this is kind of a silly picture, but imagine that I have like some surfaces. So these are my MI surfaces. And I don't know, like imagine this is like genus I or something. And imagine I have like a little base frame, which is an orthonormal basis for some tangent space here. Then as I goes to infinity, you should sort of be imagining these surfaces as converging to some infinite volume thing that is, like a surface with an infinite genus. Okay. And the point is that, if I sort of look at, if I look at a ball, like for Ri, like this, the ball around the base point with a radius Ri is going to look something like this for large I, right? So this you could take to be BM F Ri, and you can see that that this thing then pulls back. I mean, this thing embeds in all the approximating MIs for large I, and it sort of embeds almost isometrically. Okay, I mean, it's kind of in my picture. It looks like as soon as I is bigger than 4 or something, then you can see this red thing inside of it. Okay. Does this make sense? So this is a notion of convergence that, which space is this convergence happening in? Well, this, I mean, I guess we'll talk about this sort of later, but you can make a space of framed manifolds, of framed Riemannian manifolds, and then, I mean, this is the convergence on that space. Like I'm giving you what it means for a framed Riemannian, a sequence of framed Riemannian manifolds to converge to a limit framed Riemannian manifold, and so this is like the notion of convergence on that space. Okay. Right, and then so what's the how does this relate to Chabauty convergence? Well, so let's fix a base frame. Maybe I'll call it fx for x. Then so then I get a map from sub df g to framed X manifolds, MF, and I can consider these framed X manifolds sort of up to framed isometry. Okay, so framed isometry here just means like you have an isometry between one manifold and the other manifold that sends one base frame to the other base frame. And I can, what's this map? So if I have gamma, then I can map that to the pair like X mod gamma, so just the quotient manifold. And then, well, maybe I'll write the frame as, I don't know, gamma fx. I mean, whatever this is just like you take the base frame for H2 and then you project it to the quotient manifold. So this is the projection of fx to the quotient. Okay. So like I fixed a base frame somewhere in here's my little base frame somewhere in the for some tangent space to x, and then I project that to the quotient manifold, and then I get not just a manifold as a quotient, but I get a framed manifold as a quotient. So that gives me this map here. And the theorem is that this is a homeomorphism onto its image. Okay. Right. So in other words, like, yeah, I can view Chabauty convergence as exactly this smooth convergence of framed manifolds, at least when I'm looking at discrete torsion-free subgroups. And so, maybe one thing, like you might be wondering what's up with homeomorphism onto its image. Well, so a lot of times when you're thinking of things in terms of framed convergence, like hyperbolic space is a natural world to play in, but and when G is like the isometry group of Hn, so X is Hn, this map is surjective. So it's actually a homeomorphism, not just a homeomorphism onto its image. Right, but so in general, that's not the case, though. So in general, it's not surjective. And I mean, the point is basically that yeah, it comes down to the point that G may not act transitively on the like frame bundle of X. Okay, so you can look at the frame bundle of X, which is just like all the different frames that you can put at different points of X, and G in general doesn't act transitively on that. I mean, if it does, then the space has constant curvature, and you're basically looking at hyperbolic space. Yeah, so it's, I mean, somehow the fact that it's not surjective in general doesn't really cause any problems. It's just, you know, not all possible frames for these X manifolds arise. Okay. But most of the examples, the geometric examples we'll be doing are in HN anyway, in which case you do have a homeomorphism. Okay. And then I guess I should also say, yeah, maybe like this interpretation of the Chabauty topology. On like the space of subgroups of the symmetry group of HN, sort of interpreted geometrically as above, or, you know, even interpreted geometrically slightly differently. Is, you know, really important you know, when in low dimensions, so like when n is 2 or 3, say. You know, for instance, in you know, this kind of geometric convergence is a key tool in Thurston's you know, program to solve his geometrization conjecture. Yeah. Hey, so let me ask, when I don't actually remember when I'm supposed to stop talking. And have
you have another 25 minutes.
Okay, so if I talk for another 10 minutes and then have a couple of questions,
that's totally fine. That's totally fine. Yeah, yeah.
Okay, cool. All right. So maybe what I'll do then is, let me give you a another case study of like what sub G looks like for maybe a more interesting group than the real numbers or R2. Okay, so here's a case study. So we're going to set G to be, how about the orientation preserving isometry group of H2, which is the same as PSL2R. And I'm going to try to describe to you what sub G looks like. So read the question about the theorem. Yeah, so, well, right. I mean, so in order to have some sort of convergence of manifolds, it's sort of it's crucial to have some sort of base point or base frame or something. So, I mean, if you try to define this kind of smooth convergence without taking a base point or base frame, then I mean, you get something horrible, some like sort of non-Hausdorff horrible crap. So like, so it's important to sort of have some sort of base point or base frame, and yeah, and the point here is that like the fact that we're using frames here, like you could do this whole theory with base points instead of base frames, for instance, and you'd get like a pointed version of smooth convergence. And the reason why we don't do that in the theorem is because then the map that we're constructing would not be injective. Okay, so the frames sort of allow this to be an injective map. I mean, it all sort of comes down to the fact that that if you have an isometry of Riemannian manifolds that fixes a base frame, then the isometry is the identity. Or I mean, sorry, what am I talking about? Yeah, right. If you have an isometry from Riemannian manifold to itself that fixes a base frame, then that isometry is the identity. Okay, so that's I mean, you can sort of imagine that in R2, right? Like, imagine I have an isometry of R2 and it like fixes this base frame. Okay, then what can it be? It can't. It can only be the identity. So that's sort of the whole reason why we're using frames here instead of base points. You know, because there are lots of isometries that fix a base point. You know, like take a rotation around that base point. Okay, so what's this case study? So I guess I should mention that you know, a lot of what I'll talk about here is like this is actually joint work in progress with Nir Lazarovich and Ariel Leitner. Maybe I'll call us BLL. So, all right. So what does sub G look like? And so it turns out that, you know, closed subgroups of G are either they're either discrete, elementary. So what's elementary meaning? That means that they have a finite orbit in H2 union boundary H2, or they're or they're equal to G. Okay, so, and you know, all right, maybe the elementary assumption doesn't mean much to you right now if you don't study hyperbolic geometry, but the point is that elementary groups you can completely classify because, you know, they're elementary. So, you know, what are the elementary groups? Maybe I can just say examples include for instance, the group A of gamma of you know, translations of all translations along a geodesic gamma in H2. So if I have a geodesic in H2, I can look at all translations along it. That's this A of gamma. You know, I can look at the group U of Q of all parabolic isometries fixing a point Q in boundary H2, or I can look at like the group of rotations around a given point. So the group K of P of rotations around some P in H2. And you know, there's some others. I mean, but I can list like all the isometry types. So you can have like, you know, there are cyclic groups, infinite dihedral groups, groups that are the affine, that are isomorphic to the affine group, R semidirect R, and also ones that are isomorphic to R semidirect Z. And you know, the point is somehow that the topology, you know, on the space of elementary groups is completely understood. And maybe just as one example of convergence, if I have a sequence of geodesics that sort of converges to a point Q in the boundary of H2, then the corresponding sequence of groups AN converge to U of Q. Okay, so the sort of picture to have in mind here is something like, here's your Q, and then I have some sequence of geodesics, and they're sort of converging down to Q. And then if I take all the, these groups of translations along these geodesics, then they converge to this group of parabolic isometries fixing this Q. Okay, and then, maybe I'll just say, so the first paper to sort of describe this topology was by Bike and Clavier in maybe 2013. So they sort of describe the topology on a subspace of this space of elementary groups, and you can see our paper when it comes out soon for sort of a description of the complete topology. Okay, I mean, it's a little bit too complicated for me to draw a picture of it for you, but but there's nothing mysterious about it. It's just like you have all these different classes of groups, and they fit together in a way that you can describe. Okay. So maybe let me talk to you about the discrete groups though, because that's much more interesting. Okay, so discrete groups gamma in G correspond to well, framed hyperbolic two orbifolds. Okay, so here it's like orbifold instead of manifold because the groups don't have to be torsion free. So that there's a similar theory to what I just described without the torsion free assumption. But if you're uncomfortable with the word orbifold, just like pretend everything's torsion free and pretend we're talking about hyperbolic surfaces. And then so what sort of discrete groups do you have? Well, for every topological like two orbifold or surface, if you're thinking about the torsion free case. So with finite topological type, so we're thinking of like a closed surface minus a few points. So we can let sub GS be equal to all gamma, where the quotient H2 mod gamma is homeomorphic to S and has finite volume. And then this is a subset of sub G. Okay, so in other words, essentially what I'm looking at now is like all framed hyperbolic two orbifolds that have this given homeomorphism type. And so, this sub GS, this is sort of a framed version of the moduli space like MS of all finite volume hyperbolic structures on S. And, you know, and also like the map. So I can look at the map from sub GS to this moduli space, which just takes a group gamma to the quotient. So, you know, if you're thinking about base frames, this is like sort of taking the framed manifold and forgetting the base frame. And so this map is like a fiber Orbi bundle. So, you know, it's like it's a fiber bundle like in the category of orbifolds, which moduli space is. And this sub GS, so it turns out this is like a manifold of dimension equal to the dimension of moduli space plus 3. Okay, so yeah, so what am I talking about here? So like for each topological 2 orbifold, then I can sort of look at the space of all framed hyperbolic orbifolds homeomorphic to that, and that gives you some subset of sub G, which it turns out is a manifold of this dimension. Okay, and so here is sub G. So what does sub G look like then? It contains, you know, the elementary groups. Yeah, the way you should think about it is you have this sort of subset, this easily understood subset of elementary groups. All these infinitely many finite dimensional framed moduli spaces. Sub GS. But then there's also tons of like groups gamma. So these are discrete groups in where the quotients are infinite type surfaces. Or you know, or orbifolds. Okay, so these easily understood elementary groups, these sort of finite dimensional moduli spaces, the framed moduli spaces, and then this huge zoo of like of groups where the quotients are infinite type. And maybe just to end with the theorem. So here's one thing that we prove. So I mean, this is like a short theorem, you know, like a few page theorem. So the path components. So we characterize the path components of sub G. So there's like the singleton set G. There are the spaces sub SG, where S is a sphere with 3 cone points. And there's everything else. So maybe I can say like the component sub 1G of the identity. Okay, but really the point is that, okay, there's G, that's a path component, then there's like all these path components that come from spheres with 3 cone points, and then everything else is connected. And our conjecture, which we're working on and presumably hopefully we'll write down a proof of by the end of the year, is that this last component is simply connected. Okay, and I guess I'll stop there. But questions?
All right. Thank you, Ian, for the wonderful lucid talk. So yeah, so are there questions for you?
Yeah, so in higher dimensions, so dimensions say greater than 3, is it known that lattices are isolated? Or discrete sub? Yeah, yeah. Okay.
They are, yeah. I mean, the lattices, right? I mean, this is must have rigidity, essentially.
Yeah, but say in dimension 3, you still have, say, you can still do the stain filling. So you have these uniform lattices converging to non-uniform lattice. So beyond that, I mean, is there some statement to say that you can't converge as?
Yeah, there is. I mean, it's right. I mean, maybe the right thing to say is to cite Wong's finiteness theorem.
That's right. That's right. Okay. Yeah. Okay.
Yeah, I mean, for other people, that just says that there are finitely many isometry types of hyperbolic n manifolds with volume less than some given bound, and that works for n at least 4.
Any other questions for Jan?
Is there any heuristic for the dimension count?
Say again, sorry.
Is there any heuristic for the dimension count? I was just trying to see if. This is for sub SG.
Oh yeah, right. Yeah, well, I mean, the point for the dimension there is just that. I mean, you have this fiber Orby bundle structure, and it turns out that the fibers are 3-dimensional, and so that's why you get dim m of s plus 3, because I mean it's like a fiber bundle where the base is moduli space and the fibers are 3-dimensional, and so you get this dim m of s plus 3.
Okay.
Yeah, but the reason why the fibers are 3-dimensional is because yeah, what are the fibers here? The fibers are just like, I fix a hyperbolic surface or orbifold or whatever, and then I'm supposed to look at the space of all, like, what are all the different frames that I can pick for that orbifold? And if I'm looking at like a 2-dimensional orbifold, so say a hyperbolic surface, then how do you make a frame? You just make a frame by picking a point and then picking a unit vector, and then like taking the and then you take one of the 2 choices of orthogonal vectors. Okay, and so how many degrees of freedom are there? Well, the S has 2 dimensions, so I get to pick the point which has 2 dimensions, and then I need to pick a unit vector at that point that's 3 dimensions, and then the other element of the frame is sort of determined. I mean, I guess it's either this one or that one if I'm allowing frames of sort of arbitrary orientation.
Right. Yeah, thank you. That makes sense.
Yeah, cool.
Yeah, so I have a question. So if you take G to be a semi-simple Lie group, for example, and if you look at the let's a sequence of closed subgroups converge, if you look at a sequence of closed connected subgroups, so can you say something about that, whether it converges to some connected subgroups or not?
Yeah, I mean, I guess the limit will always be connected, I think. Yeah, I mean,
is there any result like that?
Yeah, I mean, I think you could just prove that. I mean, right. I mean, okay. I guess you have to say something, right? You can't just take a sort of a limit of paths, because you need to say that the paths don't go to infinity, or that paths sort of don't get longer and longer in your sequence. But yeah, no, I'm sure this is just a. Okay, I guess I'm blanking on how to write that down right now, but I'm sure it's true.
Yeah,
I'm sure it's not hard either.
Okay. And also for this convergence of this frame Riemannian manifold. So could you mention some reference for that part?
Yeah, right. I mean, I think the right things to look at for this are okay. So there's two papers that sort of do this kind of stuff. There's okay. There's this paper with 1 billion authors. So this is right, this paper by Miklos and me and Nicolas Bergeron and Tsahik Gelander and Nikolai Nikolov and Jean Rameau and Ido Samet from 17, published in 17. It's like on the right, what do we call it? Like on limits of I can't remember the name of the paper.
Is this something like L2 invariants of?
Yeah, right. Limits of L2 invariants for lattices in Lie groups or something. So there's that paper, and that does some of this, and then you can also check out this paper I wrote with Miklos, which is unimodular measures on the space of Riemannian manifolds. And that sort of, I mean, the latter paper I think goes more deeply into this stuff, but the 7-author paper was first, I guess.
Any more questions? All right, if not, then let's thank Ian again.